adequately go across the deck with flanges staggered as the cross-section goes through. So to undertake the analysis, the conventional way would be with a grillage model, but it was also decided that a three-dimensional finite element model would be carried out to be able to look at the interaction between the deck slab and the beams in a bit more detail for this possible settlement and build-up of stresses within the structure. Modelled to achieve the grillage was also the bracing as a separate frame model, to be able to look at the loads within that and the stiffness of the frame. And then again there was a numerous modelling for the settlement cases. A typical grillage model using an influence surface to determine where to load the deck. This is one which was carried out for one of the abutment bracings, and the bracings on the left-hand side of the screen. But you can see from the influence surface that to get a critical load case for that bracing, in fact only half of the deck needed to be loaded with the live load. And so in terms of actually correctly modelling the loads that needed to come into place, numerous models needed to be carried out to see which were critical for different settlements combined with different loading, different live loading onto the deck. Typically for a large bridge of this type, it's a fairly flexible deck, and you can see from this an edge beam influence surface the loading which maximises that sagging moment within the edge beam doesn't actually need live loading on the other side of the deck. So it was a case of looking into detail at where the loads would be placed for these cases and also the settlement cases as well. The bracing frame model was used as a two-dimensional frame with elements representing the bracing members and the effective members of the stiffeners. This was used as sort of a cantilever model to determine a stiffness for the shear flexibility and the bending flexibility of the frame itself. So those parameters could be put into the grillage model so that it would run with a reasonable, appropriate level of stiffness for the bracing, such that the output would be able to be fed back into this model and we could look at the loads within the bracings, the concern being that the bracings would be undergoing potential movement with that settlement. And then a 3D finite element analysis was done, a pretty coloured picture for the screen. It was done to look at the build-up of stresses as the various deck elements were cast. This is between two of the deck pours. It looked at the way in which the stresses sort of interface between the deck and the steel beams itself. The conclusion of the structural analysis was that, in fact, the size of this bridge helps us. The 60-metre span means that it's a flexible structure, and in fact having that flexibility means that the settlement that occurs between abutments can be accommodated quite well, because the twisting that could go in the structure isn't particularly overstressed. Something of interesting that came out from it was in fact that the grillage analysis was very, very good in comparison to the 3D finite element analysis, and that something to take forward is maybe that the 3D analysis wasn't actually needed. The degree of accuracy didn't really provide any improvement on the grillage analysis. Being involved in the Category 3 check, most of the background work had obviously been done beforehand, and working with the designers, the main thing that was found was that the bracings that were needed for the erection of the structure to be tolerance ties between the beams and the bracing for the brace pairs to lift in were actually the elements that were overstressed when the bridge was in service. Nowadays you would look to design these elements so that they would be left in place to avoid the erectors of the steel having to go back and remove elements. But in fact, by stiffening up bracing elements, in this case with that distribution of the loading, actually meant that they attracted more load and you couldn't you couldn't get away with it really. So the decision was taken that in fact the bracing needed to be removed afterwards. So I hope this appears on the screen. It's slightly grey, but this is the construction process that Sergio described. It started off with the sheet piles being put in for the scow wall, and then the deck to the bridge cast in a conventional manner. As you would expect, the starter bars for the bearing shelf and the abutment wall were in place. The next stage, though, was to cast the bearing shelves, but the abutment walls, the wing walls, and the cattle creep in a slightly later time were cast to part height. The reason for doing that was that we could get fill behind the abutments. On the west abutment, on the left-hand side, you can see the fill is going in there, which is putting load onto the abutments early during the construction stage and so starting the settlement process. But it also means that if the abutments settle, the reinforcement, we haven't determined the top of the bridge at this stage, and the reinforcement were designed such that the laps would have a degree of movement in them, and that the wall could be set to a higher level to accommodate the settlement that had taken place during the work. The crane was the other significant factor in terms of the loading on it. The cattle underpass on the east abutment meant that there was another obstacle to overcome, but before that could be built, the crane needed to get in as close as possible to lift the beams into position. 60-metre long beams, it's quite a long reach to take a braced pair in. And there was potential for a 400-ton load from an outrigger of a crane, which would be on the back of the abutment to be loading that base during the erection process. And in fact, it was something that was fed back into the geotechnical design as to how that sequencing of events would happen, such that 400 tons could be accommodated and the settlement would occur with loads being put on at the front and the back of the base. The beams were lifted into position but placed on temporary jacks. The temporary jacks would mean that the level of the beams could be lifted incorrectly, but if there was settlement, they could always be trimmed into the correct place as the construction progressed, because of the risk that one corner may go down compared to another. That level could be kept. And then when the deck was cast, the final construction could be brought up to the correct level. One reason for doing this was in terms of restrictions on where the deck could be. The Environment Agency had said that there was no allowance for having a central pier, and every little bit of capacity was needed in the case of flooding for water to go underneath the bridge. So the soffit level was a very determined value, and it's fairly flat through the valley at that point. And so the vertical curve on the highway meant that the top level of the deck was also a limitation, and really for the span that was needed to cross the river, we needed that for the construction depth. So the decision not to build it higher and allow it to settle needed to be moved away from, and we needed to build it at the right height once the settlement had occurred during construction. The deck was constructed in a standard sort of manner with 3 phases, the ends being cast before the centre, so as to reduce the locking in of the sagging moment within the single span. And then finally the bridge deck could be lifted to the appropriate position. The settlement now occurred, the bridge deck and its complete slab has been cast. There's been fill on the abutments for the duration of the construction as well, and the cattle underpass has been cast. So the final process would be to grout up the bearings on the beams, and then the final little bit of fill at the ends of the deck and the run-on slabs. So that was the construction plan, and this is the way in which it was carried out on site. The scow wall had to be the first to go in, and that was constructed on both sides. There was talk of piles going down rather easily as one was driven. 1 3 away would go down and 1 4 away would pop up, but they went in. You can maybe just see on this picture something that gives this the size of the spanaway. On the far side of the river is the other abutment. It's very small, and in the distance it's quite a big span. The Environment Agency stipulated that once the pile wall was in, no construction works could be undertaken on the other side of that wall. And although there was a lot of discussion and requests to be able to do works on the other side, there was no ability to do that. So the conventional way to make an integral connection between the top of the piles and the base slab would be to have a capping beam with link bars going through the piles with holes burnt through. But that wasn't allowed because the capping beam would be on the other side of the pile wall. So the solution was to devise a method, and the reinforcing bars for the base were actually welded to the pans of the pile. I've included this in the talk as an indication of something maybe not to do in the future. We've tried it, and it takes a long time to weld the bars on, especially with weather hampering the effects. Plus the alignment of the reinforcement. It's very nice for steel fixers to have a lovely square grid to lay things out to, and as the pile line curves round, to get that square grid was difficult. So as an interesting point of how not to do it next time, it's to push the Environment Agency that bit further to say we need to build a capping beam and get a different connection. But it was completed. The contractor got the base down, and this is the first lift for an abutment. So you can see that it's more than a kicker. It's come up to half the height of the reinforcement cage, such that they could extend the cage to the finished level once settlement had occurred. To lift the beams in, we designed for the 400-ton load on the back of the abutment, but we'd also suggested that bracing needed to be removed because it was being overstressed. The fabricator and erector for the steelwork Fairfield Maybe decided that in fact the craneage cost for that large crane for the paired lift was so much that they could do it in a more efficient manner by doing a lift of a single beam at a time. And structural engineers amongst you will know that single beams are notoriously unstable, and that's why the brace pair is lifted in. And so there was a need for temporary works to be able to cope with that lift of a single beam. And the trestling in the foreground of this photograph is temporary works to accommodate that. And when the beam was lifted in, you can see on the right hand side there a small RSJ that spans from the temporary works across to the top of the beam. And there were 2 of these, one from each side of the river, and they stabilised the top flange so that a single beam could be lifted, and before it was taken away from the crane, released from the crane, the temporary works would be in place. You can see a bit more detail as the second beam comes in, the trestling there, and the actual formation of that trestling and the need on site to run the beam across was actually more economic than getting the larger crane in for the 500-ton lift. During the design stage, the intention was that the beams would be landed onto jacks, so there would be that variability of height. The contractor rationalised things and took a gamble that settlement wouldn't be too significant or too differential, and chose to land them on hardwood timber blocks with a little bit of visqueen on top. You can see it just at the back of the beam there, the blue visqueen, and the final bearing was in place on the bottom of the beam, but it wasn't grouted up. It was just held in position while settlement went on. And it proved to be an acceptable way. There was always provision to lift that up had there been the need, but the contractor went for the hardwood block, and it worked. This is a photograph that's taken through the end screen wall of the abutment. It's looking at the back of the bridge deck, again to indicate the fact that that hadn't been cast. Normally you would have cast that element in one go and then lifted the beams into place. Beyond the reinforcement, you may be able to see the bracing, which is the diaphragm bracing, which conventionally you would expect to see quite a deep diaphragm through there, something which is normally used for temporary jacks for changing bearings. The width of the bearing shelf was designed so that the bearings could be changed, and in fact a lighter bracing arrangement was used at the diaphragm to allow for possible flexibility and differential settlement. The cantilever for the bridge, as well as having the twist in it and the skew in it, has a curve of the highway in plan as well, and although the beams are straight. And to achieve that, originally we looked at having a precast cantilever unit to be able to progress the works quickly. But because of them being cast with straight lines and the size of the bridge, the concern for a threepenny bit effect was such that we went back to having a cast in situ edge to the bridge. The deck was cast using FRP permanent formwork with a steel rib within the FRP to strengthen it for permanent formwork. This photograph I've included for the formwork, but also to really indicate the size of that top flange which is there for the beam, and the shear studs which needed to be quite tall shear studs to accommodate that stepping of the beams for the cross fall across the deck to ensure that the reinforcement could run through on straight bars underneath the head of the studs of the shear studs. And then the cantilever again there completed with a smooth line on it, and you can see how close the bridge is over the river and the need for that flooding area really, and no central pier. This is the sort of final stages of completion for the bridge, and indicates the cattle underpass. The underpass was a late addition. It was something that allows the farmer to get his cattle or bison, if you know the area there, under the bridge. You can see in front of there isn't much distance between the soffit of the beams and the river, whereas the arch bridges of the old structure do allow cattle to go underneath. So it gives that provision. The photograph also gives a little bit of context again for the size of the beams. The chap in the underpass with the yellow vest on is a normal sized chap. This is the completed structure. You can see how close it sits to the existing bridge, and prior to the works happening, the consideration for the effects of construction on that existing bridge was something that needed to be taken into account. And so before work started, in fact, vibration monitoring was placed on the existing structure, a couple of points on the bridge, and they took some background readings prior to construction, and those movements were placed in the contract as a limitation for what the degree of movement allowable would be. And during the piling operation, which was the main concern for it, they didn't reach or go near those values that were picked up on the bridge, which actually seemed to occur with the passing of HGVs, and probably due to the slight hump in the bridge and possible lift off of an axle of an HGV going over the bridge. I said I'd put in some other aspects of the structure. I like these because it puts into context the A5, this new structure that's been built, but it's part of the history of Telford's A5, a topic of civils talks before. Within the area there is one of Telford's gates, a gate designed by Telford for the A5, and in fact a lot of the work went into the refurbishing of the gate and new gate posts for the gateway there. There is a farm field gate post with 1826 etched into the top of it, the date of the A5. It's the date at which the the Menai Straits Bridge was opened, and a milestone. And all of these, historic, important elements of the works were incorporated into the boundary walls of the new job. Something that most people will whiz through and never know. But if you care to stop and have a look, they're there still to be savoured. And I'll now pass on to Chris, who will go back to the geotechnical outcome.
Right, thanks very much. Just to sort of now pick up really on having talked about the structural considerations and the background to the geotechnical decisions, just to pick up on what actually happened and perhaps to step back a little bit and look at the strategy and the success of the strategy as we see it. During construction, what happened was a series of settlements occurred obviously at the different stages. Initially we had about 8 mil differential movement between the abutments after installation of the girders. That was when the temporary jacks were in place. There was then a 9 mil differential movement between the abutments after the backfill to the structure. And then finally, at the final stage, before the bearings were grouted up, there was no actual differential movements between the abutments, but there was about 8 mil total settlement. And overall, there was about 15 mil torsional settlements between the abutments. I think when we then stand back and look at those, obviously we had predicted originally quite significant settlements. The total measured settlement of 15 mil was within those, which was good. But those settlements have been determined using quite conservative soil parameters, and there were obviously good reasons for doing that, given the implications for getting it wrong the other way, and the uncertainty of the behaviour of the rigged silts. What's interesting is that if we then went back to the load test and we used much more empirical measures that you might use for a less sensitive structure, Burland and Burbridge, what actually transpires is that the settlements you would calculate with that are much more in line with what we achieved directly from the load tests. So 20 mil settlement short term, 30 mil long term. But the important thing is that the differential settlements overall were less than the 20 millimetres required tolerance for the grouting of the bearings. So I think what was important to realise is that there was a very considered strategy behind all of this, in terms of identifying very early on that there were significant uncertainties with the behaviour of these silts, and that there were considerable risks attached to them, as we've tried to indicate. The potential of getting that issue of settlement, movement, bearing capacity wrong would obviously be catastrophic and would affect the feasibility of the bridge overall, and certainly feasibility for using shallow foundations. So very early on, and this is to the credit of the Welsh Assembly Government, they were very keen to review those risks in detail and to develop a proper strategy for them and a proper allocation of those risks. They promoted the approach that we adopted, which was further detailed investigations and trials at some expense to look at the feasibility of shallow foundations, and as part of that, because of the level of risk, a conservative approach was adopted. Ultimately, we were able to go forward with shallow foundations as a solution because of the confidence we had based on the information that we'd obtained and the approach that we took. So this is just, I mean, I apologise for the amount of text there, and I'm not intending obviously to read it, but what it is an indication of is the fact that, not that the risks weren't similar between the two options, between shallow foundations and deep foundations, but the complexity of risks with deep foundations and the difficulty in trying to bottom some of those issues out compared to shallow foundations were one of the reasons that took us down this route of looking into the feasibility of shallow foundations, and particularly, essentially, in order to determine that we would get the capacity from deep foundations, that we wouldn't disturb the silts, that we wouldn't cause a reduction in the lateral capacity of the silts during piling. We would have pretty much had to construct a very large, very deep foundation, which would obviously been impractical. And fundamentally, we also had concerns about, if we had have gone down the route of providing a foundation that carried loads all the way through the rig sills, that we would have found it very difficult to find a competitive way of tendering for that. The shallow foundation issues, the issues we've highlighted about differential movements, disturbance, and the possibility of differential movements for whatever reason, for example, the variability of ground conditions between the different abutments, and this issue of the possibility that settlements may occur over a long period of time outside of the construction period and therefore be difficult to accommodate. Those are things which, whilst they presented significant risks, we felt that we could address by a proper strategy of investigation and by ultimately considering the construction sequence. So overall, I think it's important to recognise that the strategy for risk management, which the Welsh Assembly Government was very keen to promote, was that having done all of this investigative work and feeling that as a project team we understood the risks of the ground, was to take that risk, not to try to put that risk onto the contractor, and to manage those risks by appropriate contingencies within the project, rather than simply putting it onto somebody who has less experience of that, and consequently would ultimately potentially put inappropriate levels of risk within their tender price. So therefore, the success of that approach really was demonstrated was despite the fact that considerable expense had been put onto these additional investigations and load tests over what you might attempt to do for less complex structures, there was actually an overall saving as a result of that strategy, and consequently it does provide a good model. This project does provide a good model for other schemes where there are these kinds of complex ground conditions. So in conclusion, the bridge was constructed successfully using shallow foundations on these silts which had previously been, the properties which had previously been unknown really. A full-scale field trial was essential to confirm these parameters, so quite an expensive operation was necessary to do that. But the low settlements which were ultimately achieved validated the choice of shallow foundations. Clearly they were a successful choice compared to the cost and expense of constructing deep foundations. And the bridge construction successfully accommodated the settlements during the works. So the success of the risk-focused approach really was around this issue of understanding the ground conditions and the risks and consequences of them. The level and nature of the risk justified the conservative modelling approach that we took. So despite the fact that you could go back and look at very simple ways of looking at the settlement and say, well, I could have predicted a lower level of settlement, clearly in the circumstances this conservative approach was justified because of the consequences of doing otherwise. And the successful completion of the bridge justified the decision of the Welsh Assembly Government to take ownership of these geotechnical risks and manage them in-house, as it were, rather than pushing them out onto the contractor, leading to an overall reduction in the cost of the scheme.